Okay, let's talk about implication. The arrow symbol is a logical connective that represents implication. P arrow Q is a symbolic abbreviation for many equivalent statements in mathematics, such as P implies Q, P entails Q, if P then Q, and many more. The power of implication comes from the modus ponens rule of deduction, which says simply, if you know P and P implies Q hold, then for sure you know Q holds. Implication has a transitive property, so that if you have a cascade of steps in a long mathematical argument, all glued together with implication, then knowing the first step is true sets off a chain reaction, and you have a rock-solid, gold standard guarantee that the last step is true. Now, implication is a sophisticated connective. We have simpler connectives such as not for negation, and for conjunction or for disjunction, and each has a truth table that tells you how to process truth values when the connective is applied. For negation, we use the tilde symbol and we have a single variable P that can be true or false. If P is true, then not P is false. If P is false, then not P is true. The truth values flip over. For conjunction, we use a wedge symbol and have two variables P and Q, each of which can be true or false, giving rise to four possible combinations. P and Q is true precisely when P and Q are both true, false otherwise. For disjunction, we use a V symbol, and by contrast, P or Q is false only when P and Q are both false, and true otherwise. Now we can combine connectives to build compound expressions and use the previous tables to evaluate truth values. So here we have a table with columns for not P, not Q, P and Q, the negation of P and Q, and not P or not Q. In the first row, P and Q are both true, so not P and not Q are false. P and Q is true, its negation is false, and not P or not Q is false. You can check in the second, third, and fourth rows that both formulae evaluate to true. Thus their columns of truth values are identical. When this happens, the formulae are said to be logically equivalent, denoted symbolically by a three-stroke equal sign. Here, not P and Q and not P or not Q are logically equivalent. This is one of the famous laws of De Morgan. So what about the truth table for implication? Again, we have four rows corresponding to different combinations of truth values for P and Q. When P and Q are both true, then P implies Q should be true. It would make no sense to assign P implies Q the value false. In the second row, when P is true and Q is false, it makes no sense to say that the truth of P entails the truth of Q. So P implies Q must be false. What about the third and fourth rows when P is false? It's no longer intuitively clear, so we put question marks and call these X in the third row and Y in the fourth row. So X is one of T or F, we're not sure which, and Y is one of T or F, we're not sure which. Now we can figure out what X and Y should be by considering two important notions, the converse and the contrapositive. The converse of P implies Q is Q implies P, the result of interchanging the hypothesis and the conclusion. And these should not be logically equivalent. For example, if I'm in Sydney, then I'm in Australia, is a true implication. The converse, if I'm in Australia, then I'm in Sydney, is patently false. You can easily imagine being in Australia without being in Sydney. Hence, P implies Q and Q implies P should not carry the same information. They should not be logically equivalent. Now, the contrapositive of P implies Q is not Q implies not P. the result of interchanging the hypothesis and conclusion, but also negating them. And on reflection, these should convey the same information, so should be logically equivalent. For example, saying, if I'm in Sydney, then I'm in Australia, is an implication that carries the same information, though expressed differently, as saying, if I'm not in Australia, then I'm not in Sydney. To model mathematics correctly, we want P implies Q and not Q implies not P to be logically equivalent. So let's build the truth table for the contrapositive. Remember, in the truth table for P implies Q, we have T and F in the first and second rows, and then these mysterious values X and Y in the third and the fourth rows. In the first row, P and Q are both true, so not Q and not P are both false, giving the pattern FF, which corresponds to Y. In the second row, not Q is true, not P is false, so we reproduce the pattern TF, which yields F. In the third row, not Q is false, not P is true, so we reproduce the pattern FT, which yields X. In the fourth row, not Q and not P are both true, so we get the pattern TT, which yields T. Now the columns for P implies Q and its contrapositive have to coincide since they're logically equivalent. And you can see that we're forced to conclude that Y is equal to T. Now let's see what happens with the truth table for the converse, Q implies P. In the first row, Q and P are true, so we have the pattern TT, which yields T. In the second row, Q is false, whilst P is true, so we have the pattern FT, which yields X. In the third row, Q is true, P is false, so we get TF, which yields F. In the fourth row, Q and P are both F, so we get FF, which yields T. If we put these columns together, we see that they coincide if X equals F. But remember, they're not logically equivalent, so we must have disagreement. This forces X to be different from F, and so we conclude that X is equal to T. Okay, since we now know that X and Y are both equal to T, we get the full truth table for implication. When the hypothesis P is false, the third and fourth rows of the table, then we say the implication P implies Q is vacuously true, regardless of the truth value of the conclusion Q. Right? If pigs can fly, then cows can jump over the moon. Clearly pigs can't fly, so if they could, then anything would be possible, no matter how absurd. If you're bothered by vacuously true implication, or generally feel uncomfortable when you first start using mathematical implication, don't worry. You can easily check that the truth table for the compound proposition, not P or Q, has an identical column of truth values. Thus, P implies Q is logically equivalent to not P or Q. If in doubt when doing mathematics, just think of P implies Q as meaning either P is false or Q is true, and you won't go wrong. Thank you.